Hello everyone, I am Priya from BSc Chemistry Honors Final Year. Today I am going to present a video for visually impaired students. The name of unit is Photochemistry and this is taken from our Physical Chemistry 2 and this book is from Pradeep's edition. So now introduction. Interaction of radiation with matter. Photochemistry is defined as that branch of chemistry which deals with the study of interaction of radiation with matter resulting into a physical change or into a chemical reaction called photochemical reaction whose rates and mechanisms are studied after initiation by the radiant energy. Though the term radiation includes all types of electromagnetic waves from very low frequency microwaves to medium frequency infrared, visible and ultraviolet radiation to high frequency X-rays and gamma rays. The radiation of photochemical importance are those which lie in the visible and ultraviolet region from 8,000 to 2,000 angstrom. Thus, the two main process studies under photochemistry are photochemical process or photochemical reactions. Photophysical process. Photophysical process are those processes which take place in the presence of light but do not result into any chemical reaction. These processes arise on account of the absorption of light by the substances followed by the emission of the absorbed light. If the absorbed light is emitted instantaneously, the process is called fluorescence. If the absorbed light is emitted after some time lag, the process is called photophorescence. Further, if the energy of the light absorbed is sufficiently high, the electrons may not only jump to the outer levels but may leave the atoms completely. The process is called photoelectric effect. Thus, photophysical process include phenomena like fluorescence, phosphorescence, and photoelectric effect. Photochemical reactions are those reactions which take place by absorption of light by the reactant substances. These reactions are generally brought about the absorption of light radiations of the visible and ultraviolet region which lie between 8,000 to 2,000 angstrom. As already mentioned above, in these cases the light energy absorbed is stored within the substances and then used for bringing about the reaction. A large number of different types of reactions can be brought about by exposure to suitable light like synthesis, decomposition, oxidation, reduction, polymerization, isomeric change, etc. Two well-known examples of photochemical reactions are given below. Combination of hydrogen and chlorine to form hydrogen chloride. H2Cl2 makes 2HCl. Photosynthesis of carbohydrates in plants taking place in presence of chlorophyll, the green coloring matter present in the leaves. It may be pointed out that the photochemical reactions takes place when incident photon has sufficient energy so that it can result in the excitation of one the reactants from ground electronic state to excited electronic state, as will be discussed later in the chapter. Difference between photochemical reactions and thermochemical reactions. The main points of difference a thermochemical reactions and photochemical reaction are summed up. Thermochemical reactions. These reactions involve absorption of heat. They can take place even in the dark. Temperature has significant effect on the rate of a thermochemical reaction. The free energy change of a thermochemical reaction is always negative. Photochemical reaction. These reactions involve absorption of light. The presence of light is a primary requisite for the reaction to take place. Temperature has very little effect on the rate of a photochemical reaction. Instead, the intensity of light has a marked effect on the rate of a photochemical reaction. The free energy change del G of a photochemical reaction may not be negative. A few examples of photochemical reactions for which del G is positive and still they are spontaneous are synthesis of carbohydrates in plants, ozonination of oxygen, decomposition of HCl into H2 and Cl2. For thermochemical reaction, in these reactions, activation energy arises from the intermolecular collisions or it is supplied in the form of heat. Photochemical reaction. In these reactions, activation energy is required by absorption of photons of suitable energy. In thermochemical reaction, when a reaction mixture is exposed to heat radiation, all the reactant molecules absorb these reaction radiations and get excited almost to the same extent. There is no selectivity. When a reaction mixture is exposed to light radiation, the molecules of one of the reactants may get excited independent of the presence of other species molecules in a mixture of H2 and B. In the present chapter, we shall discuss mainly the laws of photochemistry, examples of some photochemical reactions, the mechanism by which they proceed, and certain terms like fluorescein, phosphorescein, and chemiluminescence. Laws covering absorption of light. When a monochromatic light is passed through a medium, some light is absorbed by the medium and hence the intensity of the incident light decreases. The decrease of intensity on passing through a pure homogeneous medium is governed by Lambert's law, and the decrease of intensity on passing through a solution is governed by Beer's law. Lambert's law. This law put forward by Lambert state as under: when a monochromatic light is passed through a pure homogeneous medium, the decrease in the intensity of light with the thickness of the absorbing medium at any point x is proportional to the intensity of the incident light. The intensity of light at point x mathematically minus d of I upon dx is directly proportional to I, or minus di upon dx is equal to ki, where di is the small decrease in intensity of the light on passing through a small thickness dx. I is the intensity of the incident light just before entering the thickness dx, and the constant of proportionality k is called the absorption coefficient depending upon the nature of the absorbing medium. The intensity I at any point x can be found in terms of the original intensity I naught as follows. Equation 1 can be written as di upon I is equal to minus k of dx, where x is equal to 0, I is equal to I naught, x is equal to x, I is equal to I. Integrating equation 2 between the limits x is equal to 0 to x and I is equal to I naught to I, we get I equal to I naught e की power minus kx. This equation expresses how the original intensity I naught is reduced to intensity I after passing through a thickness x of the medium. The difference between I naught and I obviously gives the intensity of the light absorbed. Thus, I absorbed is equal to I naught minus I is equal to I naught minus I naught e की power minus kx. Equation 4 can be expressed in another form, which can be derived as follows. Equation 3 can be written as 2.303 log of I upon I naught is equal to minus of kx, or log of I upon I naught is equal to minus k dash x, or I is equal to I naught into 10 to the power minus k dash x, where k dash is equal to k upon 2.303 is called extinction coefficient of the substance. Now it is a quantity which is called absorption coefficient or absorptivity of the substance. The physical significance of the extinction coefficient or absorptivity follows more clearly from equation 6, which can be rewritten as k dash is equal to minus of kx minus of 1 upon x log of I upon I naught is equal to 1 upon x log of I naught upon I. Hence, extinction coefficient or absorptivity may be defined as follows. The extinction coefficient or absorptivity is the reciprocal of that layer thickness at which the intensity of the light falls to 1/10 of its original value. Beer's law. This is an extension of Lambert's law put forward by Beer. It is applicable to solution and states as under: when a monochromatic light is passed through a solution, the decrease in the intensity of light with the thickness of the solution is directly proportional not only to the intensity of the incident light but also to the concentration C of the solution. Thus, for a solution, mathematically we have minus di upon dx is directly proportional to I into C, minus di upon dx is equal to gamma IC, where psi is the constant of proportionality and is called molar absorption coefficient. Its value depends upon the nature of absorbing solute and the wavelength of the light used. Equation 8 can be rewritten as di upon I is equal to minus psi c dx. As before, integrating this equation between the limits x is equal to 0 to x and I is equal to I naught to I, we get I is equal to I naught e की power minus psi cx. This equation shows that the intensity of a monochromatic light decreases exponentially from I naught to I with increase in thickness x and concentration c. The intensity of the light absorbed by the solution when it passes through a length x of the solution will be given by, as before, equation 9 can be expressed in another form. For the purpose, we can rewrite equation 9 as, and finally we get I is equal to I naught into 10 to the power minus psi dash cx, where psi dash is equal to psi upon 2.303 was earlier called molar extinction coefficient of the absorbing solution. Now it is the quantitative which is called molar absorption coefficient or molar absorptivity of the absorbing solution. The physical significance of molar extinction coefficient or molar absorptivity follows from equation 13, which can be written as psi dash is equal to minus 1 upon cx log of 1 upon I upon I naught is equal to 1 upon cx log of I naught upon I. Hence, molar extinction coefficient or molar absorptivity may be defined as the reciprocal of that thickness of the solution layer of 1 molar concentration, which reduces the intensity of the light passing through it to one tenth of its original value. It may be pointed out that gases follow Beer's law and not Lambert's law. Units of molar absorptivity or molar absorption coefficient. In SI units, X is in meters and C is in mole meter minus 3. Hence, we have, however, usually concentrations are expressed in mole little minus 1 and length X in centimeter. The units of psi C, psi dash will then be some other terms commonly used in spectrophotometry. Spectrophotometry deals with the measurement of intensity of the light absorbed when it is passed through a sample of known thickness and concentration, measuring the intensity of transmitted light relative to that of the incident light. It is especially useful when one substance in the reaction mixture has a strong absorption in the spectral range. In these studies, the following terms are commonly used: transmittance, the ratio I upon I naught, the ratio of intensity I of the transmitted light from the solution to the intensity of the incident light I naught. The fraction of the incident light transmitted is called transmittance T. Transmittance T is equal to I upon I naught. Absorbance A or optical density or extinction, the logarithm of the reciprocal of transmittance log of I upon T or log of I naught upon I is called absorbance A or extinction E. Thus absorbance is equal to extinction is equal to optical density is equal to log of I upon T is equal to log of I naught upon I. Specific extinction coefficient Ks. It is defined as the extinction or optical density or absorbance per unit length and unit concentration of the solution. Ks is equal to D upon Cx. Molar extinction coefficient. Substituting the value from equation 16 in equation 13, we get minus log of I upon I naught is equal to minus log of T is equal to A or D psi dash Cx. Thus, if x is equal to 1 centimeter and c is equal to 1 mole little inverse, psi dash is equal to d or a. Hence, molar extinction coefficient may be defined on the optical density or absorbance of the solution having 1 centimeter thickness and concentration equal to 1 mole little inverse. Thus, a plot of absorbance A versus concentration C will be a straight line passing through the origin with slope psi dash x as shown in figure 4.2. The dotted portion of the curve shows deviation from linearity at higher concentrations. Limitations of Beer's law. The law holds good only for monochromatic radiation. The law is applicable only to dilute solution. At higher concentrations, the interionic interactions disturb the absorption of incident radiation. The temperature should almost remain constant. Too much rise in temperature shifts the absorption band towards longer wavelength. Laws covering photochemical reactions. There are two important laws of photochemistry as explained below. Grothus-Draper law. This law is also called first law of photochemistry. It was put forward by Grothus or theoretical grounds and confirmed by Draper by experiment. It states as under: when light falls on a body, a part of it is reflected, a part of it is transmitted, and the rest of it is absorbed. It is only the absorbed light which is effective in bringing about a chemical reaction. The Abola, however, does not imply that the absorbed light must always result into chemical reaction. The absorbed light may simply bring about phenomena such as fluorescence, phosphorescence, etc. as already mentioned in section 4.1 and discussed later in section 4.7. Similarly, the absorbed light energy may be simply converted into thermal energy in case of potassium permanganate solution. The light energy is absorbed strongly but no chemical effect is produced. Further, in some cases, it is observed that light energy may not be absorbed by the reactant substance directly but may be absorbed by some other substance present along with the reacting substance. The energy thus absorbed is then passed on to the reacting substance which then starts reacting. This process is called photosensitization and has been discussed in details in section 4.11. A well-known example is that of photosynthesis of carbohydrates in plants where chlorophyll acts as a photosensitizer. The expression for the light absorbed when it passes through a pure liquid or through a solution have already been derived in section 4.3. Stark-Einstein's law of photochemical equivalence. This law is also called second law of photochemistry. It was put forward by Einstein and Stark. It states as under: every atom or molecule that takes part in a photochemical reaction absorbs one quantum of the radiation to which the substance is exposed. If V is the frequency of the absorbed radiation, then the energy absorbed by each reacting atom or molecule is one quantum. HV H mu, where H is Planck's constant, the energy absorbed by one mole of the reacting molecules will then be given by E is equals to NH mu, where N is Avogadro number. Putting mu is equal to C upon lambda, we can write E is equals to NHC upon lambda, where C is the velocity of light and lambda is the wavelength of the absorption radiation. The energy possessed by one mole of photons is called 1 Einstein. Numerical value of Einstein in different units. In CGS unit, substituting N is equal to 6.022 into 10 to the power 23 mole inverse, H is equal to 6.623 into 10 to the power minus 23 ERG second, and C is equal to 3.0 into 10 to the power 10 centimeter per second. We will get E is equal to 2.86 upon lambda in centimeter calorie per mole. In this equation, lambda is expressed in centimeter. However, as lambda is usually expressed in angstrom units A, and we know that 1 angstrom is equal to 10 to the power minus 8 centimeter, therefore equation 3 can be written as E is equal to 2.86 upon lambda into 10 to the power 8 calorie per mole, where lambda is in angstrom. Further, putting 10 to the power 3 calories equal to 1 kcal, equation 4 can be written as E is equal to 2.86 into 10 to the power 5 upon lambda angstrom k calorie per mole. In SI units, we substitute N is equal to 6.22 into 6.022 into 10 to the power 23 mole inverse, H is equal to 6.626 into 10 to the power minus 34 joule second, C is equal to 3.0 into 10 to the power 8 meter second inverse. We get E is equal to 0.1197 upon lambda in meter. In this equation, lambda is in meters. The unit of energy used most frequently in photochemistry is electron volt, EV. 1 EV is equal to 1.602 into 10 to the power minus 19 joule. Thus, the energy per Einstein is inversely proportional to the wavelength of the radiation. Shorter the wavelength of a radiation, greater is the energy per Einstein. For example, the order of wavelength of different radiation is X-rays, then ultraviolet, then visible, then infrared. Hence, the energies per Einstein of these radiations are in the order X-rays greater than ultraviolet, greater than visible, greater than infrared. Interpretation of Einstein's law. Introduction of the term quantum efficiency. In Einstein's law is correct. If Einstein's law is correct, every reacting molecule will absorb one quantum of radiation. Hence, the number of reacting molecules should be equal to the number of quanta absorbed. However, it is found that in a number of cases, a small amount of the light absorbed can bring about a large amount of reaction, whereas in some other cases, large amount of the light absorbed can bring about only a small amount of reaction. This was explained on the basis that all the molecules present do not absorb the radiation. First, only a few molecules absorb the radiation. These molecules are said to have been activated. These activated molecules then react with the other molecules and thus bring about a large amount of chemical reaction. On the other hand, in certain cases, the activated molecules get deactivated and no further reaction takes place. The first stage is called the primary process. The reactions involved in the second stage are called secondary process. To relate the number of quanta absorbed with the number of reacting molecules, a term called quantum efficiency or quantum yield has been introduced. It is expressed as psi is equal to number of molecules reacting in a given time upon number of quanta of light absorbed in the same time. Means number of moles reacting in a given time upon number of Einsteins of light absorbed in the same time. Hence, quantum efficiency may be defined as the number of moles reacting per Einstein of the light absorbed. If Stark's-Einstein's law is strictly obeyed in the form already stated, psi should be equal to unity. However, studies have shown that the law is applicable only to primary process. Hence, it is sometimes preferred to state it as follows. Each molecule that gets activated to initiate the reaction absorbs one quantum of light. Experimental determination of quantum yield or a quantum yield of a photochemical reaction. Theory of the process. For experimental purpose, the expression for the quantum yield may be written as psi is equal to number of moles reacting per second upon number of quanta absorbed per second, rate of chemical reaction per quanta absorbed per second. Thus, to determine the quantum yield of any photochemical reaction, we have to measure the rate of chemical reaction in terms of molecules per second, the quanta absorbed per second. Apparatus. The apparatus used for measuring the above two quantities is shown in figure 4.3. It consists of the following parts from left to right. A source of radiation emitting radiation of suitable intensity in the desired spectral range. The commonly used sources are filament lamps, carbon metal arcs and various gas discharge tubes. Lens of suitable focal length, monochromator or filter which cuts off all radiations except the radiation of the desired wavelength. Still, to get a fine beam, a cell placed in thermostat and containing the reaction mixture. The cell is made of glass or quartz and has optically plain windows for the entrance and exit of light. Glass is used only if the wavelength of the light used lies in the visible range. For radiation with the wavelength below 3500 angstrom, the cell completely made of quartz is used. Recorder. It is usually a thermopile or an actinometer which is used to measure intensity of the radiation. The principle of a thermopile and that of an actinometer are briefly explained below. A thermopile is a set of thermocouples. Rods of two different metals are joined alternatively as shown in figure 4.4. If only two rods are connected, it constitutes a thermocouple. One set of junctions is soldered to metal strip blackened with platinum or lamped black, and the other set of junctions is protected completely from radiation by placing the system in a box as shown in figure 4.4. The radiations falling on the blackened metal strip are almost completely absorbed by it. As a result, this set of junctions becomes hot. The temperature difference of the hot and the cold and produces a current which can be measured by connecting a milliammeter to the thermopile. By calibrating the thermopile with radiations of known intensity, the intensity of the desired radiation can be measured. A chemical actinometer in a device in which gas mixture or solutions sensitive to light are used. The working of this device is based upon the fact that a definite amount of radiation absorbed brings about a definite amount of chemical reaction. The most commonly employed is a uranyl oxalate actinometer, which consists of 0.05 molar oxalic acid and 0.01 molar uranyl sulfide solutions in water. When exposed to light, the following reaction takes place. Uranyl sulfate acts as a photosanitizer. The extent of reaction is measured by titrating the oxalic acid solution with potassium permanganate solution. The actinometer is first calibrated against a thermopile. This actinometer can be used for measuring only the intensity of the radiation lying in the range 2000 to 5000 angstrom. Procedure: measurement of the intensity of light absorbed. First, the empty cell or the cell filled with solvent alone is placed in the thermostat. The monochromatic radiation is allowed to pass through the cell for a definite time. The reading is taken on the recorder. From this we get the energy of the incident radiation. Now the reactants are taken in the cell and the radiations are allowed to pass through it for definite time and the reading is taken again. The difference between the two readings gives the total energy absorbed by the reactants in a given time. From this, the intensity of the radiation absorbed IABS is calculated to as follows: total energy absorbed upon volume of the reaction mixture into time in second. Measurement of the rate of reaction. The rate of reaction can be studied as usual. For this purpose, either the change in some physical properties followed or samples of the reaction mixture are removed periodically from the cell and analyzed. Knowing the rate of reaction and the intensity of light absorbed, the quantum yield of the reaction can be calculated. Some examples of photochemical reactions. Based upon the quantum yields, the various photochemical reactions have been divided into three categories as summarized in table 4.2 on the next page along with the examples. The wavelength of incident radiations and the approximate quantum yields. Thus, from the table, it is obvious that the quantum yields of photochemical reactions vary within very wide limits from 0.01 for the photosynthesis of HBr to 10 to the power 6 for the combination of hydrogen and chlorine. The reason for very high or very low quantum yield has already been discussed, wherein it was stated that a photochemical reaction takes place in two steps, which are primary process that involve the activation of certain molecules by absorption of light, 1 quantum per molecule. Ab plus H makes AB, activated molecule. On the dissociation of certain molecules to produce active atoms or free radical. Secondary process. This involves the reaction of the activated molecules or the products of the primary process with other molecules or the deactivation of the activated molecules. To illustrate the mechanism by which photochemical reactions proceed, a few examples are briefly discussed below. Photolysis of hydrogen iodide. The photolysis of Hi to give H2 and I2 has been studied in the wavelength range 2070 to 2820 angstrom and the quantum yield of this reaction has been found to be approximately 2. This has been explained by proposing the following mechanism for the photolysis of Hi. Primary process: Hi plus H mu makes H plus I free radical. A molecule of Hi absorbs one photon of light and dissociates to give a normal hydrogen atom and an excited iodine atom. Secondary process: the products of the primary process then take part in the secondary process as follows. All these secondary processes are not important. The reactions third and fifth are highly exothermic and the heat produced results into the dissociation of the products of these reactions. Reaction second is endothermic and hence takes place slowly. Thus, the only secondary process of importance are the reaction first and fourth, rewriting the reaction of the primary process and the two important reactions 1 and 4th of the secondary process. We have adding these three equations we get the overall reaction 2Hi plus H mu makes H2 plus I2. Thus, for every 1 quantum of light absorbed, the 2 molecules of Hi are decomposed, hence the quantum yield value of 2 is justified. The quantum yield for the photolysis of HBr is also 2. It has therefore been suggested that the mechanism of this reaction is exactly similar to that of photolysis of Hi as discussed above. Second, photosynthesis of HBr, photochemical combination of hydrogen and bromine to form HBr. The reaction may be represented as H2 plus Br to HBr. The quantum efficiency of this reaction is very low, about 0.01 at ordinary temperatures. This is explained by proposing the following mechanism for the above reaction. Primary process Br2 plus H mu 2Br. Secondary process Br plus H2 HBr plus H Br plus Br2. The H atom produced in reaction 1 attacks Br2 according to reaction 2 producing HBr and Br atom. The Br atom thus produced attacks more of H2 according to reaction 1 producing H atom again. As a result, reactions 1 and 2 should repeat over and again. A chain reaction should be set up and the quantum yield of the reaction should be very high, but actually the quantum yield is very low. This is explained as follows. Reaction 1 is endothermic and hence takes place slowly or almost does not tend to take place. The reaction 2 and third 2 and 3 depends upon the formation of H atoms in reaction 1. Consequently, reaction 2 and 3 are very low. So the only reaction of importance is the secondary process is the reaction 4th. This is just the reversal of primary process. Thus the Br atom formed in the primary process do not combine to form HBr. Instead, they combine together to give back Br2. As a result, the quantum yield of the reaction is very low at ordinary temperatures. The quantum yield of the above reaction increases with increase of temperature. This is obviously because of the fact that the reaction 1, which is endothermic and requires high energy of activation, becomes faster at high temperatures because the required energy of activation becomes available at higher temperature. Photosynthesis of HCl from H2 and Cl2. This is an example of a reaction whose quantum yield is very high. This reaction may be represented as H2 plus Cl2 in presence of H mu makes 2HCl. The high quantum yield of this reaction is explained by the chain mechanism. The different steps involved are as follows. Primary process Cl2 plus H mu makes 2Cl. Chain initiating step. A chlorine molecule absorbs one quantum of light and dissociates to give Cl atoms. The H atom produced in reaction 1 attacks Cl2 according to reaction 2 producing HCl and Cl atom. The chlorine atom thus produced attacks more of H2 according to reaction 1 producing H atom again. In this way, the reactions 1 and 2 repeat over and again till almost whole of H2 and Cl2 have reacted to form HCl. The reaction stops when the chlorine atoms left of combine with each other to form Cl2. According to reaction 3, this reaction takes place on the walls of the reaction vessel. It is a common practice to call the reaction of the primary process as the chain initiating step, reactions 1 and 2 of the secondary processes as the chain propagating steps, and the reaction 3 as the chain terminating step. It is interesting to note that the mechanism of the above reaction is similar to that of the photosynthesis of HBr, yet the quantum yield of this reaction is very high, whereas that of photosynthesis of HBr is very low. The difference is explained on the basis of the reaction 1 of the secondary process. In the present reaction, the reaction 1 of the secondary process which immediately follows the primary process is exothermic and therefore takes place very easily, and consequently the chain reaction is set up very easily. In the photosynthesis of HBr, the reaction 1 of the secondary process is endothermic and thus has very little tendency to take place. The quantum yield of the above reaction decreases if the reaction vessel contains small traces of oxygen. This is explained on the basis that oxygen leads to the chain termination by the following reactions. The chain mechanism for the photosynthesis of HCl as discussed above is further supported by the following facts. The reaction can be brought about without exposing the reaction mixture to light but by simply adding some chlorine or hydrogen atoms into the reaction mixture. The quantum yield of the reaction decreases considerably if the reaction is carried out in capillary tubes. This confirms that the chains are terminating on the walls of the reaction vessel. So far we have described one more example of each type of photochemical reaction. Now we shall take up the discussion of a few more common photochemical reactions. Photolysis of ammonia. This is an example of a photochemical reaction whose quantum yield is very low, about 0.25 at ordinary temperatures and pressures. The probable mechanism is supposed to be as follows. In primary process, NH3 plus H mu makes NH2 plus H. The presence of H atoms has been proved by suitable methods. Secondary process. The ultimate products of the photolysis of ammonia have been found to be nitrogen, hydrogen and hydrazine. Hence, the following probable secondary reactions have been proposed. Since the quantum yield of the reaction is very low, the reaction 1 and third takes place only to a very small extent. The important secondary reaction is the reaction fourth, only which involves the reversal of the primary process. Photolysis of acetone. The reaction may be represented as CH3COOCH3 in presence of HMO gives us C2H6 ethane plus CO carbon monoxide. The main products of the photolysis of ammonia are ethane and carbon monoxide, but small amounts of methane and appreciable amounts of diacetyl are also found to be present. The quantum yield of the reaction is found to be nearly unity. All these observations suggest the following probable mechanism for the above reaction. Thus, no chain reaction is set up. The free radicals formed in the primary process simply react with each other. Hence, the quantum efficiency of reaction is unity. Photolysis of acetaldehyde. When acetaldehyde is irradiated by UV light of radiation, it breaks up into radicals which start the chain reaction. The probable mechanism is as follows. Primary process CH3CHO plus H mu CH3CHO. Secondary process CH3 dot CH3CHO CH4 plus CH3CO CH3CO dot CH3 dot plus CO. Luminescence. When a solid body, a piece of iron is heated, it first becomes red hot and then becomes white hot, and hence it begins to glow. The glow can be produced by methods other than the action of heat. When the excited electrons jump back to the inner levels, light is emitted. The light thus produced is called cold light. The glow produced in a body by methods other than the action of heat, the production of cold light is called luminescence. The body emitting the cold light is called luminescent. Luminescence may be any one of the following three types. Chemiluminescence. When a photochemical reaction takes place, light is absorbed. However, there are certain reactions in which light is produced. The emission of light in chemical reactions at ordinary temperatures is called chemiluminescence. Thus, chemiluminescence is just the reverse of a photochemical reaction. A few examples of chemiluminescence are as under: the light emitted by glowworms is due to the oxidation of the protein luciferin present in the glowworms by atmospheric oxygen in the presence of the enzyme luciferase. The oxidation of yellow phosphorus in oxygen or air to give P2O5 at ordinary temperatures is accompanied by the emission of visible greenish white luminescence. Oxidation of decaying wood containing certain forms of bacteria also produces luminescence. In all the above cases, a part or a whole of the energy emitting during the reaction, instead of appearing as heat, is used up for the excitation of electrons, which when jump back to the inner orbits results into the emission of light. Fluorescence. There are certain substances which when exposed to light or certain other radiations absorb the energy and then immediately or instantly start re-emitting the energy. Such substances are called fluorescent substances, and the phenomena is called fluorescence. Obviously, the absorption of the energy results into the excitation of the electrons, followed immediately by the jumping back of the excited electrons to the lower levels. As a result, the absorbed emitted energy is back. The word instantaneous used above implies that the time between the absorption of the energy and the re-emission of the absorbed energy is not more than 10 to the power minus 8 seconds. Thus, fluorescence starts as soon as the substance is exposed to light, and the fluorescence stops as soon as the light is cut off. A few examples of substances showing the phenomena of fluorescence are fluoride, certain organic dyes such as eosine, fluorescence, vapor of sodium mercury iodine, certain inorganic compounds such as uranyl sulfate. It is interesting to observe that in the phenomena of fluorescence, the wavelength of the emitted light is usually greater than that of the absorbed light. This is explained on the basis that the energy absorbed raises the electron to a sufficiently higher level, but the return of the excited electron to the original level takes place in steps through the intermediate levels. The energy thus produced in every jump is smaller, and hence the wavelength of the light emitted is larger than that of absorbed light.